Got it? All right. I'll begin with a word of prayer. Dearly Father, we thank you for this day. I just pray that you'd help us to understand more about your creation today and this time we have together, and that you'd give us clarity of thought and just continue to encourage students as they work on this course just to do their best, Lord, each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, so some of you are like, I'm not convinced. You told me before that you think that Calculus 3 would really be a wise prerequisite for this course, but I'm not really convinced that that's the case. Could you show me more evidence of that? Well, I'm glad you asked, because this is just such an occasion. Now, last time we showed that the moment of inertia for a solid sphere, right? Solid sphere, radius r, mass m. We worked it out. What was the moment of inertia? If I recall correctly, it was 2/5 mr squared. That's the moment of inertia for a solid sphere. We showed that last time by calculus. I mean, excuse me. There's going to be a lot of that today. But then somebody asked me, like, is the sphere solid, or are you talking about like a spherical shell? And then we got to thinking, like, how would this be different if it was just a spherical shell? What if it was just, what if it's like this, but if you were to take a little cutaway, it's just, just like the outer surface of a gobstopper or something, Remove the inside, it's a shell or a basketball. There you go. Right, a basketball has, the outside has mass, but the inside is essentially massless, right? Just air, hardly anything there. So what would the moment of inertia for a spherical shell be? Well, in order to calculate that, you really need to be able to do the following integral, right? It should be equal to the integral over the shell, right? Of what is it? R squared dm. And so just to picture what's going on here, so if I think about this being the axis of rotation, right? I'm thinking about a little piece of area out here. This is my little dm, and it's a distance r away from the axis of rotation. Now that r, if I use x, y, z coordinates, right, then of course r is equal to the square root of x squared plus y squared, just to be precise, right? So how do you do such an integral? Well, the way you do it is you rewrite. Now we're assuming a uniform mass density, right? Uniform mass density. Otherwise, the problem would, not be so simple. So what that means is that dm ds, where here capital DS is the surface area. I'm saying that the little bit of surface area that I'm thinking about subtending has a little mass dm attached to it, and dm ds, well, that's the mass per surface area, right? Now, if the mass per surface area is uniform, that means that the total mass divided by the total surface area should also be equal to this instantaneous rate of change, right? So this should also be equal to what? The total mass, which is m. What's the total surface area? What's the surface area of a sphere? Indeed, it is 4 pi r squared. Now, some of you don't know that. That's okay. You should take Calculus 3. You'll derive it there. So there you go. That's the relation between. So I can solve. So what I have is I've got dm is equal to big M over 4 pi r squared ds, right? Okay, so I can trade this, see, for an integral over the shell. what? Of r squared times m over 4 pi r squared ds. Then the question then is, of course, how do you do such an integral? Well, we talk about that in Calculus 3. This is called a scalar surface integral. And long story short, what you do is you find a parameterization for the sphere. In this case, it would be r of, say, phi theta equals to r cosine theta sine phi, r sine theta sine phi, r cosine phi, and you calculate then that the ds is actually what it's defined to be is the square root of partial r partial phi cross partial r partial theta d phi d theta. It turns out when you calculate that, I'm not gonna. Well, I mean, I guess I could give you a little geometric argument for why I'm going to write what I'm going to write. So let's see here. X is equal to what? X is equal to r cosine theta sine phi. Y is equal to r sine theta sine phi. So you put this together, what's x squared plus y squared equal to? Pull that constant out front. You notice what happens? I got a cosine squared, I got a sine squared. So I end up with what? R squared sine squared phi. So in other words, the ds, all right, works out to, well, I haven't, so I'm sorry, one thing at a time here. R squared, this r squared, which again is x squared plus y squared, right? That is exactly r squared sine squared phi. The ds, on the other hand, you calculate this parameterization, you take the cross product of those partial velocities, and what you get, the magnitude of that, I'm sorry, I'm missing some, doesn't make sense to take the square root of a vector, does it? I should really just say what here? Sorry, guys. What would make more sense is the magnitude. I was thinking about writing the square root of the sums of the squares when I wrote the square root there, and then I decided against it. The magnitude of that works out to, well, let me try to give you a short explanation for why that is what it is. If you look at the sphere, right, and you look at the little patch like this. So what I'm saying is that it's coming from a little d phi, and then also, I can't illustrate it worth anything. So this is the patch I'm getting from rotating a little. Let me remind you where phi and theta are. Phi is like this. Theta's down here. So what I want to think about is let theta go to like theta plus d theta, right? And let phi go to, say, you know, this would have phi plus d phi. And so that would sweep out this little, like, I'm not very good at drawing this, but I'm trying, this little patch up here that corresponds to subtending d phi and d theta. What's the length, let's say, of the, what's the length of this piece? I can project it down here. This would be what? This is like, what's the length of this radius down here? This radius down here is, that's r sine phi. So the length of the the little length corresponding to the theta sweeping out is r sine phi d theta. And the length of the little red lines here, what's the length of the red radius here? That's just r, because we're on the sphere. So that's sweeping along a radius r. In my picture over here, these are the red ones, and excuse me, these are the green ones. So the arc length subtended along the phi displacement is just r d phi, because you have that radius and that angle subtended, right? So the area ds, basically, if you just want to argue by geometry, ds is equal to dl theta dl phi, right? So what I'm telling you is, yeah, Calculus 3 says this is a calculational scheme you can use to derive it from vector calculus like this. When you work out the details, you just get what geometry indicates to you from base principles, which is that it's r squared sine phi d theta. Let me make that purple. Separated here. So that gives me r squared sine phi d theta. Oops, but I better write d theta d phi given my order of integrations. All right, long story short, we got ourselves a m over 4 pi r squared. Looks to me like I have an r to the 4th. And I've got, let's see here, if you understand Calculus 3, this is the integral from 0 to pi of sine cubed phi d phi times the integral from 0 to 2 pi of d theta. Well, the d theta integral I hope we can all do. So this gives me 2 pi, right? So I've got m over 2 r squared times the integral of sine cubed from 0 to pi. What's that? So let's see, we're making u equals cosine substitution. You get 1 minus u squared times minus du. This gives me the integral of u squared minus 1 du, which gives me 1/3 sine cubed phi, 1/3 cosine cubed phi minus cosine phi plus a constant. I'm supposed to integrate this from 0 to 2 pi, 0 to pi. Sorry, I'm trying to get the number as fast as I can. What happens when you evaluate this at pi? You get 1/3 of minus 1 minus a minus 1 minus parentheses 1/3 minus 1, which is what? This chair is taking all the fun out of it. All right, I'll behave. This gives me 2/3. This gives me 2/3. So this integral is 4/3, yeah? And what do we get? 2/3, right? M r squared there is the moment of inertia for a hollow sphere. Does it make sense? 2/3 versus 2/5. Which has, given the same mass, which would be easier to roll, to start rolling? A solid bowling ball or a solid basketball with the same mass? I mean, it's hard to, I don't think we really have much experience. Maybe you should think about like Man, I don't know if there's anything from your experience that would be a good thing to bounce off of. But it's in fact, given the same mass, it's harder to start rolling something where all of the mass is on the edge. It has a larger moment of inertia. This is like a 0.66. This is 0.4. So it's about 50% more inertia for a given mass and radius there, right? In terms of rotational things, it's about 50% heavier in the rotational world. That makes sense because more of the mass is further away from the rotation axis, right, as opposed to a solid sphere where there's more mass close to where you're rotating, which means it has smaller inertia. Right? More mass further away from the axis of rotation gives you a larger inertia. All right. Well, let me work a couple of examples. Now, obviously, I won't ask you to reproduce this on the test because I shouldn't, because that would be mean, because Calculus 3 is, in fact, not a prerequisite for this class. And so the necessary skill set to really do this, you may or may not have. You may have had Calculus 3 and still can't do this. If that's the case, shame on you. Sorry. The last statement was not necessary, but it felt good. No. There's a lot of different kinds of integrations we go over in Calculus 3. You have area integrals, you got volume integrals. You've got scalar surface integrals like this. There's also the flux integrals at the end, right? The flux integrals we don't need too much in here, but those are especially important next semester. The flux of the electric and magnetic fields are crucial to understanding second semester physics. So, okay, so standard example. So you've got a ball. And it rolls without slipping. Downhill. Let's say the height of the hill is h. The question is, basically, what is Vf? And so here, Vf is the linear velocity of the thing at the end. So it's, you could also ask what's the angular velocity. So we're assuming that the ball has radius, so we're assuming that. Now you got choices, right? You could say sphere, solid, like a bowling ball. You could say it's a sphere, hollow, like a basketball. You could say it's a cylinder. Okay. You could do that. You could do solid, or you could do shell, right? You could think about all these different cases. Each one of these different cases comes with a different moment of inertia. It's a slightly different problem. Like the sphere, let's suppose radius r, mass m. So let's recap. What's the moment of inertia for a sphere, a solid sphere? Right, 2/5 mr squared. Worked that out last time. We just worked out the moment of inertia for hollow sphere is 2/3 mr squared. We worked out the cylinder, solid, is 1/2 mr squared. And we don't need calculus to figure this out. The last one, I, is mr squared. Because a cylindrical shell would just be like, I can't draw it worth anything today. Sad. So the point is, if it's rotating around that axis, all mass radius r from rotation axis, right? So the moment of inertia is just the total mass times r squared. This integration is a yawn. It's just r is constant. You pull it out, integrate over m gives you m. Excuse me. All right. So why do we care about moment of inertia? Well, here's how you solve the problem. If it's rolling without slipping, we're assuming that there's no rolling friction. You say, why are you assuming there's no rolling friction? Well, I've mentioned to you guys before, I only have a master's in physics. Rolling friction is too hard for me. I don't understand it, so I can't cover it in here. So there's that. Or it could just be that I'm lazy. Probably that I'm lazy. But anyway, we don't consider rolling friction in here. So there is a process by which you lose energy while you're rolling. It's a little bit more complicated. So I'm assuming that we're rolling without slipping. So that's more like what you see with a bowling ball or something on like a perfectly rigid floor. And if you just roll it slow, you notice it just keeps rolling. Right? There's very little deformation between the point of contact between the ball and the floor. That deformation between the point of contact and the floor, the fact that it's not actually in contact with a point, that it's smeared out over some region, that's where the rolling with friction comes from. And it's the deformation of the contact point that actually leads to the decrease in rotational energy. It's a somewhat complicated story how that actually all works. I don't get into that except to tell you what I just told you. We're assuming that that doesn't come into play. So it just rolls like a ball on a pool table or something, right? Just without friction. Yeah.
So if you have like two objects, mass and volume or something, is that deformation in a harder one or softer one so they're not faster? If they're both reasonably good, it's not like falling. But when one's a little softer than the other, it should slow down more.
I think the harder the object, the less the rolling friction. So like, to give a kind of ridiculous example, the rolling friction of an automobile tire is way, way bigger than the rolling friction of a train wheel. I mean, it's not a valid comparison because one is metal on metal, the other one is metal on asphalt. But if you could imagine...
Tank treads.
What's that?
Tank treads.
Tank, what are you thinking?
The treads.
Oh, tank treads?
I know those are different too, but...
Ah. Yeah, now you've changed the geometry on me, so I don't even know. I don't know. Means of comparison there. But anyway, rolling with friction just means what? It means that rolling without slipping means that the arc length that's subtended by the rolling object is equal to the linear length that's rolled out. So what that means is that there's a relation between... If I could take the number of thetas, if I could take the change in theta here, so if this was, say, L would be equal to R times the change in theta. If we think about the number of times it rolls, the number of radians that the thing rolls through, if you set up the angle, measuring the angle by some fixed, maybe this is a point, you focus on that point, right? And then when it gets down to here, you're still looking at a vertical axis, and you're like the point's gone to here or whatever. And maybe it's rolled through 3 times, and it's gone a little bit more. So you measure the angle relative to some fixed axis, which kind of moves along with it, and that's what I mean by how many theta. You kind of know what I mean without me defining it precisely, though, right? If I have a bowling ball and I set it down and I roll it, and you see the finger holes. Suppose the finger holes fixed in orientation and you see them pass 4 times, and the finger holes end up in the same place they were when they started and ended. You'd know that that's 4 times 2 pi, that's 8 pi radians that the ball's rotated through, right? Even though I never defined carefully how I'm defining that rotating angle. It's not the picture we had at the start, right? Because the picture we had at the start, there's a fixed axis and we're talking about the polar angle. Right? I just changed the game on you. I'm talking about the angle relative to some moving coordinate system. Right? So see, you guys can do that. I'm getting off topic. So, the point is rolling without slipping. Means there's a connection between the final angular linear velocity and the final angular... there's a connection between... Let me get to the point here. Omega f is equal to how The final angular velocity is related to the final linear velocity. How? It's Vf over r, right? So if I take the final linear velocity and divide by the radius, that gives me the number of radians per second. Let's assume that it starts from rest, all right? And then you let it go, and it rolls down the hill without friction. How fast is it going this way when it gets to the bottom of the hill? We all understand the parameters of the problem now? Do you guys? So if it's rolling without friction, rolling without slipping, rather, it's a conservative process. So what we can do is we can conserve energy. And so conservation of energy looks like the following. It looks like mgh. This is the initial energy, right? What should that be equal to? And this goes back to that derivation I did the other day. I showed you for a system of particles that are rigidly attached and rotating around some axis, you can decompose their energy into two pieces, a translational piece and a rotational piece. The rotational piece, the value of it is governed by the moment of inertia. The translational piece, well, that's just the center of mass motion. In that case, that's 1/2, I should use capital M, sorry, 1/2 m Vf squared, right? Plus the rotational kinetic energy, which is 1/2 I omega f squared. This is the setup for this problem, whether it's a sphere or a spherical shell, or a cylinder or a cylindrical shell. It's all the same setup, it's just different moments of inertia. In fact, I don't even have to tell you what the shape of the ball is. I could just tell you its moment of inertia and reasonably ask this question. I've done that in the past. Does that make sense? So let's just pick one to work out. What do you guys want to do? Choose your adventure. Stop. Oh, what is it? Oh, solid sphere. Okay, that one. So, mgh. And I'm interested, I asked what was Vf, right? So I want to remove the omega f. How do I rewrite omega f in terms of Vf? Oh, here it is, right? Well, isn't that convenient? See what happens here? The r's cancel. And you're just left with what? And in fact, I didn't even need to tell you the mass, right? Masses cancel too. And so we just get Vf is equal to the square root. What's 1/2 plus 1/5? Would you agree with 7/10? So if I multiply it to the other side, I get 10/7. So 10 gh over 7, yeah. How does this work out if there's no moment of inertia? I mean, if there's no rotational motion, if it's just sort of like a box sliding along without any rotational component to its energy.
So you're saying it's skidding?
Yeah, suppose it's just skidding without friction, but smoothly sliding, let's say. Skidding it makes me think friction. Skidding without friction. Seems like a bad choice in terms. But that would just leave us this term, right? So perhaps you remember this example before was just like square root of 2gh, right? That's what this looks like without the rotational motion.
Wouldn't you just treat it just like you always did, like a particle?
Right. How does that compare? How does the final speed compare then without rotational versus with rotational? How is 10 over 7 compared to 2? Of course it's smaller, right? And that makes sense because some of your energy is tied up in this rotational mode. So the energy, the potential energy, has to be shared between the translational kinetic energy and the rotational kinetic energy. Both of these sectors eat up some of the potential energy, and thus the translational speed is actually smaller than it would be if there wasn't this rotational sector of energy, you could say. Does that make sense? I mean, I think it makes, to me, it makes intuitive sense that the speed should be smaller. It takes some energy to start the rotation. It's good? Well. So there are more I have a bunch of examples I'll show you on the projector. I want to talk about the the remaining laws of rotational physics. And I'll try to, well, I probably couldn't derive them today if I tried, so let me just not try, spare you the tragedy of watching me try to do it today. But there is another concept, definition, torque. All right, so what is torque? We use the symbol tau for this. It's equal to R cross F. Now this is the three-dimensional. I'll start out three-dimensionally and then I'm going to specialize, all right? So that's the cross product. So just for an example, if this is my origin and this is my radius vector, if I apply a force like this here, what's the torque produced? Now here's the pivot point. Torque has to be measured relative to some pivot point. This R is the so-called radial arm. Right. So let's see here. Remember cross product? So we do R. We cross into F. The torque vector for this guy points into the board. So how would I illustrate that? Something like, I mean, I would tend to think about the torque vector being at the pivot point. You could think about it being up here, whatever you want. I don't know. The point is, let's see, I do X, right? So torque into the board. On the other hand, if my radial arm looked like this, and my force applied looked like this, right? What's my torque? R crossed into F, my right hand points out at you guys. So there the torque would be coming out of the board. A stupid case. Radial arm here, force applied in this way. Indeed, the torque here would be equal to 0. Let me illustrate this for you. You can pivot the camera if you want. All right, I'm going to now close or open this door by applying force in the radial direction. It doesn't work, does it? Because there's no torque. On the other hand, torque this way, torque that way. Okay, so basically this torque, what it's doing is it's describing the portion of the force which is perpendicular to the radial arm, right? So if the force is totally parallel, the torque should be 0. What's the significance of the direction of the torque?
The X and Y components of the torque.
No. I'm talking more geometrically here for a second here. I said that the torque points into the board here, right? Look at your right hand. Watch. You gotta watch me. You gotta see me do this. If I point my thumb into the board, right? Look at my right hand, my fingers. They curl this way. See that? The way my fingers are pointing is the direction of the rotation that's produced by such a torque. Intuitively, you know that, right? If the force is going that way, it's making a rotation that goes like this, right? But let's just say that it tends to create a rotation in this direction, right? That's the resulting motion. This one, if the torque is out of the board, look at my right hand. See my fingers are curling like this. This is another right hand rule. It's creating a rotation that's like that, if unopposed. Okay, so that's what torque is, three-dimensionally. Now, usually, we just think about two-dimensional problems, right? And in two dimensions, right? You've got some pivot point, you've got some distance, r. You're applying a force at some point like this, right? Well, then you can just do two-dimensional geometry to figure it out, right? This angle you could call theta. So basically the part that produces a torque is the piece which is perpendicular to the radial arm, right? You could call it F perp. F perp would be what? Trigonometry, it would be F times what? Sorry. I'm not sure why, but this semester, it seems like every break I get sicker. By the end of the semester, there is silver lining. If this trend continues, I should be sick for graduation. That is the most awesome time to be sick. To be sick for graduation is a precious, wonderful thing. It's truly magical. I've been to graduation before. It's boring for me. Like, I already know what's going to happen. People are going to graduate. We're going to stand up. We're going to stand down. Trump's going to give a great speech. Oh, it's pretty likely, isn't it? Or maybe Sarah Palin. Maybe. I want Chuck Norris to come back. I missed that. That was before my time. We had Chuck Norris as a commencement speaker a few years back. We made that man a doctor. Chuck Norris, honorary doctorate. I think. That reminds me, TV on the average has gotten better. Anyway, sorry, I digress. This geometry tells us what? With this angle, it should be sine theta, right? Notice that I'm measuring the angle sweeping up off the radial arm. That's important. What theta means might be different in different problems. You got to think about it. However the formula you're writing comes, the formula should describe the part of the force which is perpendicular to the rotation. That's the thing, okay? Whatever your angle, however you define the angle. So anyway, long story short here, the torque is equal to what? It's equal to RF sine theta in this case, right? I don't need the cross product here per se. And if torque is greater than 0, that implies a counterclockwise torque. If the torque is less than 0, that implies a clockwise torque. You remember these things called clocks? They had arms on them, and they went one way or another depending on whether time was going forward or backward. I guess you guys haven't seen the backwards. Like, not so many of us have time traveled. But, no, you know what I'm talking about. We good on clockwise and counterclockwise? Clockwise. Clockwise, yeah. So by default, out of the board corresponds to like clockwise torques, counterclockwise torques on the page. Shut up. All right, are we good there? So what's the relation between the tangential acceleration and the torque? Remember? So like a tangential acceleration, well, the mass times the tangential acceleration should be the force in the tangential direction, right? I mean, that's just Newton's second law in the tangential direction. Supposing that that force producing the torque is all that's there. So what does this tell us about the angular acceleration? Remember, AT is equal to what? It's equal to the radius times the angular acceleration alpha. So what does that say about torque? So if we multiply Newton's second law by the radius, what do we get? Now, what do we have? This is, well, that gives me m times alpha, right? Equals to what? On the other side, we have what? Torque, I believe, right? No. No. I'm not right yet. Oh, it's just an algebra mistake. Can you guys see what I did? What's RAT? Sorry, what's RAT here? RAT is what? Yes, that's r squared alpha, right? So I should have what? I should have m r squared alpha. Wait a second. What is this mr squared? What am I talking about? I'm talking about a mass, right? A distance r from the rotation point, right? That's what? It's the moment of inertia, right? So we have I times the moment of inertia times the angular acceleration is equal to the torque. And there you have it. This is the rotational analog of Newton's second law. So the torque is equal to I alpha. Let me show you an example which puts this into practice. Let's look at Atwood's machine, but this time let's give the pulley an inertia. So the problem is this: we're considering two masses, mass 1 and mass 2, and they're hanging off a pulley. The pulley has radius r. Let's consider the pulley to be a solid cylinder of radius r and mass big M. We know that the moment of inertia is 1/2 mr squared in such a situation, right? We draw a picture of what we're doing. So we got some kind of like, I can't, just awful. I should just stop trying to draw anything. Yeah, something is not right here. How do you draw a cylinder? Goodness, fine, I give up. This is a cylinder, solid, and then hanging over it, two masses, M1, M2. And let's suppose that M1 is greater than M2, so motion is like that. So we'll choose that as the positive direction. Oh, maybe I shouldn't do that though. Other way around. Let's go the other way around. It doesn't matter which one's greater, right? But just so let's suppose the motion's gonna be like that. This pulley that they're attached to, it's like a I can't draw anything. Arr, it's bothering me. Radius r. Right, so the moment of inertia for the pulley is 1/2 mr squared. So how do you find the acceleration of such a system is the question, right? Now the rope is assumed to be hung over the pulley and it doesn't slip. But because the pulley pulls back on the rope, the tension doesn't have to be the same on the left and the right anymore. So, like, if I do the second law on M1, I've got T1 acting up, and I've got M1G going down, right? Over here, I've got the T2 going up, and I've got M2G going down. The acceleration is the same for all of them because the rope doesn't slip and it doesn't stretch. So that means that their motions are connected. They do share the same acceleration. So like getting started, I can do what we already know how to do, which is like M1A is equal to, well, T1 minus M1G, right? And M2A is equal to M2G minus T1. Now before, T2 rather, before we had that T1 equals to T2. So we just added these equations and we were done, right? But now there's another player in the game, which is the pulley itself. So on this, we have to do the rotational second law. Rotational second law says that the moment of inertia times the angular acceleration is equal to the net torque. Right, so basically what I do is I'm thinking of the rigid body of the cylinder, and then I apply Newton's second law to that. But then I multiply by r and basically run through this calculation for the system, and I can work out the same, that the net torque is equal to I times alpha. If I was more with it, I could derive that today, but I'm just claiming it's true. I worked it out for a particle, but the same thing is true for a collection of particles that are stuck together and have moment of inertia I. That's a derived result. But what's the question though is what's the net torque on this system, right? I mean, moment of inertia we've got, it's 1/2 mr squared. We worked that out before. What's the net torque? Well, there's two things that are making the pulley turn, right? If you look at it, you have over here, we've got T1 like this, right? Over here, we've got T2 like that, right? So I would point out that I alpha is equal to, now this is the question, which one of those is a positive torque, which one of those is a negative torque? It depends on our system of direction, right? So if I'm saying that alpha is lining up, I want to say that A is equal to R alpha, right? If I say that means that the rotational direction and the linear directions have to coincide in this way, right? So once I say that, that forces T2 to be a positive torque, right? I'm sorry, I should say tau 2. And then plus tau 1, let's say. But the sum of the torques, there's torque 1 and there's torque 2. The formulas for that, though, tau 2 is actually R T2. Torque 1 is minus R T1. Because this is counterclockwise torque, that's a clockwise torque. the reason I changed the initial condition so that the motion would be this way is so that my positive motion would line up with the counterclockwise direction. Just to try to make the problem a little bit, the example more natural, I did that. You don't have to make the counterclockwise direction the positive direction. That's a choice. Just like you can make the left direction the positive one and the right direction the negative one, or vice versa, right? Some of you feel the burn. You know what I'm talking about. Sorry. I know what I'm talking about. I know you guys want to make America great again. It's very exciting. I need to get one of those hats. One of my colleagues at another school actually has gotten himself a Trump hat. You know, the trucker hat?
Yeah.
And every so often he'll put it on and he'll just start spouting random nonsense like, want to make math great again. We're going to solve the quintic. We're going to go back to space. Manned mission to Jupiter. And you just keep going. You just keep making it more and more ridiculous. And the more ridiculous you can make it, the better the bit goes over. I've been told. Anyway, so this, right, you gotta see what this is. This is 1/2 m r squared alpha, right, is equal to RT2 minus RT1. Now, what I do, because I'm going to have to solve 3 equations and 3 unknowns, is I want to change this to like a corresponding linear equation. So what I do there is remember that alpha times r is equal to a, right? And then divide this equation by r. So what this gives me is 1/2, looks to me like 1/2 a, excuse me, 1/2 ma is equal to what? T2 minus T1. And then from there, it's just 3 equations, 3 unknowns, right? This and these 2, we got to solve these 3. How do you do that? Probably add equations is the easiest thing. I don't know. How do you guys want me to solve it? I don't much care. I mean, I'm going to give these numbers 1, 2, 3. If you look at 1 plus 2, what do you get? 1 plus 2 gives me m1 plus m with feet over 2 times a is equal to, what happens? The T1s cancel, right? And I'm left with T2 minus M1G. Did you guys see that? Did I say 1 plus 2? What did I mean? Oh, fine, 1 plus 2. I'll do 1 plus 2. I mean, you could do this any number of ways. 1 plus 2 gives me M1 plus M2 times A. This system is pretty easy to solve. Is equal to M2 minus M1 times G plus T1 minus T2. That's pretty nice. If you then add that to equation 3, what do you get? We get M1 plus M2 plus big M over 2 times A is equal to, you see what happens? The T1, T2s cancel. And we get our M2 minus M1 times G. And then you can solve for A. Remember, in the case that we said the pulley was massless, we didn't have this big M over 2 term, right? But that's the it's the new thing. I suppose if obviously when the pulley gets to be more massive, it slows the acceleration way down, right? Because it actually is taking It's taking work to get that pulley to rotate, and then you're taking energy to build up that rotational motion. And so as the mass is, as M2 drops, if you were to study energy conservation here, that's also an interesting story, right? Like, how does energy conservation work for this example? You guys have any questions before I go on to look at energy here? If we were to study energy conservation, what would it look like here? So what you'd have would be something like M1G H1 plus M2G H2 plus 1/2 M1 V1 squared plus 1/2 M1 V2 squared, right? Plus 1/2 I although, what's the relation between V1 and V2? If the string is not stretching, what does the relation have to be? Right. Can you have something where you have it attached by a string which is taut, and yet they have different velocities? I mean, intuitively, you should see the answer to that is no. So V1 has to equal V2. So why don't we just say V naught? And let's say omega naught. So what you're looking at is the potential energy of M1, the potential energy of M2, the kinetic energy, translational kinetic energy of M1, the translational kinetic energy of M2, 2, and then a new game in town, the rotational kinetic energy of the pulley itself. And what is that equal to? Same with, V naught going to VF, omega naught going to omega F, right? And H1 going to, say, H1F, and H2 going to H2F. So, but that's the net, mechanical energy, right? The net mechanical energy is the sum of the potential, in this case gravitational, and the linear and rotational kinetic energies. That's how that works. Any questions about this? Yep.
What is alpha?
Alpha is the angular acceleration. So it's d omega dt, which is d squared theta dt squared. So it's angular acceleration. Now, let me go back to the three-dimensional world here for just a minute. We talked about momentum, right? There's also an analog to angular momentum in the angular world. It's angular momentum. Let me show you the definition of angular momentum for a mass. How to say this? If you have a particle with velocity v and mass m, then with respect to origin, I mean, you have to pick an origin to talk about this, but the L, we use L, is equal to m r cross v. Alternatively, you could say that this is the angular momentum. So angular momentum is a vector. If you brought the m inside, what would it look like, though? Like this formula I just wrote. This is r cross what? mv, right? Which is just what? So the angular momentum